pretend like what we're doing isn't potentially calamitous and carry on. So today we're going to be looking at the Philco Predicta Tandem. Specifically, we're going to see how to make 3.5 restorable Philco Predicta Tandems into 3 working Philco Predicta Tandems. We join the process 2/3 of the way in. This cabinet here is going to be our keeper. It's the nicest of the 3. Wood itself is pretty much good as is. I may end up transplanting the grill cloth and the brass tuning knob backing plate for one from another set, but we'll cross that bridge when we come to it. Right now, I'm working on getting all of the, I'm working on getting 3 of the 4 chassis going properly. So some of you might be wondering why I can only make 3 of these 4 sets operational. Well, this might give you an idea why. This head unit has a replacement CRT in it that isn't an exact replacement. It is a compatible type that the neck is roughly an inch deeper than the factory tube. And because it's an inch deeper, the this removable plastic hatch on the back doesn't fit on in its stock mounting configuration. In order to mount it up, you have to basically space it about an inch off and add standoffs between this hatch and the main back shell of the CRT. The person who converted this set didn't mount the standoffs or the back cover. They just let the neck stick out the back, and at some point they slammed the back of the CRT neck into a wall, and this happened. The glass broke, and this CRT, which needs to be under very high vacuum to function, that vacuum has now been replaced by air from the atmosphere, which now makes the tube non-functional. And also, in the process of all that air whooshing in, it blew the phosphor off the inside of the CRT for the most part. There's still some remaining here. The phosphor is also an essential part of the CRT because it's what converts the electron beam shooting from the gun way back there. It's what converts that stream of electrons into light. And without it, you're not going to get an image, even if you resealed the tube and somehow pumped it back down to vacuum. And, well, you'd also have to do some work on the electron gun because, well, the cathode of the electron gun, which is an essential thing for electron emission, is constructed with a material that basically chemically changes when you bake it at high temperature in a vacuum. It changes at that point from a non-reactive substance to a highly reactive substance. Highly reactive with the atmosphere, but when it's in vacuum, it won't react with the atmosphere, and it'll be stable. Well, break the seal here, and all of a sudden it's reacted with the atmosphere, and it's contaminated to a useless state. There's also getter material, which is supposed to soak up excess gas molecules that vacuum pumping doesn't get, that also are ruined. And here's what a good CRT looks like. This one's pretty much restored. This is the first of the 4 that I owned, and the longest one that I've owned. I restored this several months back, and it works relatively good. It just needs a few things. It has a problem with retrace lines. When I first got it working, the horizontal was connected up backwards and I was getting mirror image pictures on the screen. I reversed the leads to the horizontal windings of the flexion yoke and was able to flip the screen around. But at that point, I believe I got much worse retrace lines than I was getting. I think what the issue with the set is that the horizontal yoke is fed by a coax. the outer shield being the return line. And I think when I flipped the wiring on the system plug on the chassis side around, what ended up occurring is that the hot lead of the deflection ended up being the shield of the coax, and that ended up radiating the horizontal signal into the video signal and other signals in the set. I'm going to try re-reversing the lines at the system plug on this chassis, and then opening up the CRT and reversing the leads inside the yoke to flip the mirror image effect and see if that reduces the retrace line issue. I was able to put in some retrace blanking, but in order to completely mute the retrace lines, the signal from the vertical used to accomplish that would start to actually black out the top half of the picture. So I had to adjust the component values to a compromise that resulted in sort of the least offensive intersection of blanking the top of the screen and reducing the retrace. But that will be after I get the third chassis of free working. So I finally got rid of the retrace lines on the oldest of the three chassis. Oldest in terms of time in my collection. The problem ended up being very simple. I'll show you the schematic of the brightness circuit. That 180K R34, some idiot replaced the R34 180K for 220K, and that old 220K from, I guess, the 60s drifted up to 240K, and apparently that was enough to make it hard to get rid of retrace lines no matter what I did to the couplet network down below it. The couplet network K6 I rebuilt with passive components, and it still didn't work, and I never bothered to check R34 until now. Now that R34 has been replaced, my old passive component replacement for K6 works just fine, so perfect. This is the best working of the three chassis in terms of video detail and audio quality. It also is the only one that's been converted to a banana plug for the HV pin of the system connector. I'm not sure how that'll do for reliability versus the original, but it probably isn't significantly worse. Here we have a mostly original chassis. As we can see that someone replaced one of the capacitors with a later style, not terribly later, probably 2 to 7 years later would be my guess. And here we have a what I believe is a open section on the I believe it's a filament dropping power resistor. Let's have a look at the schematic. Pretty sure that's this guy here, which is, yeah, that's a voltage divider for the dial light and the tuner. So we're going to have to look into that and do a recap on this set, i.e. replace all these capacitors with modern parts that aren't old and failed with age. And I'll try to show some tricks on component placement for having a clean chassis. Let's have a look up top and do some examining. The plug-in power rectifier diodes have been replaced with the later top hat style, which is okay, I guess. You can see that some of the capacitors on the circuit board have been replaced. This is an orange drop, which is a later style, and you can see how they kind of J-hooked it in on top of the board. Same with this one over here, but you can see original Bumblebee-style capacitors still exist on this television set. All those Bumblebees will have to be changed. And I'm tempted to also change these later type orange drop and maroon drop capacitors for new capacitors, just to tidy up the solder joints. There's nothing wrong with these J-hook joints. Some manufacturers, like GE, when printed circuit boards were first introduced, and these are pretty much the same generation of circuit board technology as the first ones in consumer televisions, manufacturers such as GE would recommend J-hooking in the new components after crushing the old components. Like, crush the body of the old component, but leave the leads stubs on the ends and solder the new part onto that. This guy here is interesting. I'm probably going to replace that with something neater as well. These plug-in Fusisters are high failure components in these Philco Predicta sets, particularly these sand style ones. A Fusistor is basically a sand resistor that's rated for the bare minimum of current that it needs to pass. And when an overload condition occurs, the thin resistance wire in it will end up overheating and burning open. That gives a fuse action to protect the set. This one's good, so we're just going to leave it alone. Some Predictas have a nice feature where the speaker terminals, I'm trying to figure out which they are on, I believe it's these two, where the speaker terminals from the audio output transformer are set up where the leads from the speaker actually have little plugs that plug onto the printed circuit board wire stakes. And you can just grab the speaker cables and unplug them. Whoops. Some sets don't have that, though. Some sets, they wire wrap the wires to the speaker right onto the same terminals that the transformer wires go to. And those are kind of a pain in the butt because there's no real way to detach the speaker from the chassis when you're pulling the chassis without either de-wrapping the wires, which is tricky when you've got the chassis out far enough to do that. You've got to hold the chassis and de-wrap at the same time, and it's a mess. If you've got the style with the plug-in connectors that connect to here, I would recommend using this unused terminal strip right here for the voltage doubler capacitors. Basically, you want to mount those capacitors, the large 140 microfarad capacitors, onto this terminal strip. It provides a really convenient mounting point for those. However, if your speaker is hardwired to the chassis where it's wire wrap connected, you might want to put those new doubler capacitors under chassis and instead use this blank terminal strip here as a speaker mounting terminal. You could then run wire from the printed circuit board speaker stakes over to this terminal strip here and add spade connectors onto the ends of the leads coming off your speaker and make it so that you can plug those onto this terminal strip. To give you an idea of what I'm doing, let's go look at one of the sets that I've already done. Now, I've gone through and I've replaced all the resistors that test outside of tolerance on the printed circuit board, and you can tell most of the ones I've changed because they're obviously different types. You can see here where I've mounted the 140 microfarad doubler caps. I didn't happen to have any 140s in my stash, so we're going with 147 in parallel for each individual capacitor. And this one has a different style of Fusistor on it, which also is testing good. Now, these K-networks here sometimes go bad as well. There's a whole bunch of them on this set. One here on this particular set was also bad. The SAM schematic will tell you what exactly is inside the K-network and how it's wired up. On this one, this particular K-network K1 had failed, and someone had jumped a resistor across a couple terminals on it to try to keep it running on the original part sometime probably back in the 60s, I would guess, based on the resistor they used. Since I was having some issues with this set, I decided to replace that network with discrete components based on what the schematic indicates is inside the network. It's not that hard to do. Now, as you can see, I've removed the two large can electrolytics that were in here. the one that was up in this location before is one of the ones that's above chassis now. And one of the sections of the large cane here is also moved above chassis. I also replaced all of the paper dielectric capacitors on this set with modern capacitors. One trick that makes recapping a lot easier is identifying ground stakes on terminal strips. Like for instance, I think you can see this here, this stake goes all the way down and mounts the strip to the chassis and is riveted on. This stake is effectively chassis ground. There's a second one, if you can see, there's a second one right here, and that one is also chassis ground. This capacitor, when it was the old one, the positive terminal was here, and the negative terminal was this one here, which is also a chassis ground terminal. So, when you switch out the old axial capacitor, where there's a lead on both ends, to a radial capacitor like this one, where the leads are both on one end, you can make mounting it easier and shorten the lead length by moving the ground lug from this ground lug to that ground lug. They're both ground lugs riveted to the chassis, so effectively they're the same point electrically in the set, and the set generally doesn't care which ground lug on which terminal strip you're using as the ground lug for your capacitor. This 0.22 capacitor right here, this is a ground lug right here, and this is its hot terminal, I guess you would say. Originally, the old capacitor had its hot terminal here and its ground lug way up here. And it's kind of hard to get a modern component with limited lead length to stretch that far. You kind of have to splice extra lead length onto the component leads, and it gets kind of messy. So this one you can move down to here, and you can do that with various other capacitors. I'll try to point some out a little bit later on, but this gives you a general overview of what gets done here. Also, the power switches on these Predictas fail, and I'll try to cover general repair procedure for the power switch. Basically, in a nutshell, this black plastic section in here, which you can probably barely see in the lighting that we've got, that's a bit better. That black back section is the switch. What you do is you pop off the little metal fingers that hold it on. You don't break them off, but you bend them away gently. And you can slide the whole switch assembly back and off. Now be careful, because there'll be a spring in there, and you don't want that to go shooting off and getting lost. But basically, underneath the spring and the central pivot rod assembly, there is a rotating ratcheting contact, a brass contact. You want to pull that out, sand it with something like 400 to 600 grit on the bottom surface that contacts the terminals, and then you want to also sand those terminals and clean it up really thoroughly to get charring and corrosion off of those points. Once you think you've got it clean enough, what you'll do is you'll put the spring and guts back into it and work the switch mechanism like it would be if it were attached to the pot, with an ohm meter hooked up to the terminals to check and see if the switch is actually connecting and disconnecting properly.
I have a second video that I feel better discusses how to fix Predicta power switches. I also in that video cover Predicta Tandem umbilical cable cleaning, and I have an additional video that covers Predicta safety screen cleaning. From here on out, this video may be boring to experienced television techs, as I really get into the nitty-gritty of doing an actual recap. Normally I try not to make my restoration videos all about recapping, as that's a fairly simple process. However, Philco Predictas tend to attract the novice collector demographic, people who haven't worked on tube radios or other televisions before, but have acquired one of these because they think it looks cool and would like to make it work again. So I figure I should make the latter half of this video cater to that demographic
One place we can definitely take advantage of ground lug relocation is this 0.1 600 volt capacitor. This terminal here is a ground lug. I think you can kind of sort of see. And here's its hot terminal, and its hot terminal is next to a grounded lug. So we can remove this capacitor from the set and install a new 0.1 microfarad 600 volt capacitor right across these two terminals, and that'll make wiring nicer. Okay, so we've replaced this capacitor with that capacitor, and we've relocated to a different ground terminal to make lead length nicer. Now, how you read these bumblebee style capacitors, if you're not familiar with it, is the first 3 bands correspond to capacitance in picofarad, and it's encoded in the same method as what a resistor would be. It's basically resistor color code. So we have brown, which is 1, black, which is 0, yellow, which is 4, which is 1-0, and the 4 is a power of 10 multiplier. So 10 to the 4th power is 10,000. So we have 100,000 picofarads, which is 0.1 microfarad. The 4th band here is, I believe, a tolerance band. It might in some cases be a temperature coefficient. Sometimes you get a few additional bands beyond 3. There will be a space where there's no bands, and then there will be the voltage band or bands. If there's 2 bands, it's usually a voltage above 1000 volts. If there's a single voltage band, as in the case of this, it's under 1000 volts. This one is a 600 volt because the band is blue. If the band is yellow, do we have one? No, we don't under chassis. If the band is yellow, it's 400 volts. In this case, the voltage band is red, which makes it a 200 volt. If you're not familiar with resistor color code, look it up. It's very useful in decoding these bumblebee capacitors. Other capacitors, like this electrolytic here, have the capacitance, 20 microfarad, 300 volts, listed right on it. Now, paper capacitors like this one and this guy down here are non-polarized, and you can connect the replacement either way around and it won't matter in the circuit. Now, when I say paper, I'm not referring to the material that the capacitor casing is made out of. I'm referring to the dielectric inside the capacitor between the metal foil plates which make up a capacitor. You can use a lot of different dielectrics. Back in the day when these sets were being built, paper and electrolytic dielectric were the 2 most common. There were also our mica capacitors in some sets and ceramic capacitors in some sets. Micas and ceramics typically don't fail, but in televisions, particularly in sweep circuits and circuits where there's a high voltage across the capacitor, micas will fail. Electrolytic capacitors are still made today and in common use today. They use basically a paper or fabric-like material and an oil, mineral oil, as their dielectric. The foil, unlike paper capacitors, the foil in electrolytics is not smooth, but actually a roughed up metal material which effectively increases the surface area so you can get a higher capacitance in a smaller package. The downside is that they tend to degrade pretty bad. You can get large value film capacitors that are, instead of a 0.1 like this, you could get ones that are 10 or 20 microfarads that are almost as big as this capacitor is. They'll be a lot more reliable, but they also are much larger physically than modern electrolytics of the same value, and they cost a lot more, which is the only reason why electrolytics are still used. At any rate, we're going to shift gears, and I'm going to change this capacitor next. We're going to take the negative lead, which goes to this terminal, which is effectively chassis grounded. It even connects to the electrolytic can chassis ground terminal. And we're going to move it to this ground terminal right here, and we're going to keep using the same positive terminals. Let's just go after this. I'm going to unhook the negative terminal, which is hooked to the ground lug here. We're also going to, while we're at it, go after the one on the this adjacent cap, which we'll change next. Let's just get that out of the way. And I'm going to replace this 20 microfarad 300 volt with a 22 microfarad 450 volt. The voltage rating is basically a rating of what the cap can stand up to. If I were to put, say, 600 volts across this 300 volt rated cap, it would explode. But if I were to put 100 volts across this 300 volt rated cap, it'd last forever, or at least a very long time. So, if you're selecting a replacement cap, get the same voltage or higher for safety purposes. Also, capacitance values, the standard ones that components are made in, have changed since this set was built. They were actually in transition at the time this television set was built. It has a mixture of the old and new numbering scheme.
It was at this moment that he f***ed up.
So when this set was made, you had nice round numbers for capacitance. 2, 3, 4, 5, and multiples, that power of 10 multiples thereof. So, say 20, 30, 40. Dang, this chair's creaky. Modern capacitors now have 2.2, 3.3, 4.7, and so on as modern numbering standards. So, one still exists both in the old and the new standard, which is nice. But for capacitors that are, say, 2 or 3 or what have you, you need to select the closest modern standard value for the part to use. Solder in the new cap. And the closest modern value will be within tolerance of the original part. So there won't be any issues in using the closest modern value when the old standard value is no longer in vogue. And you save money by using the modern standard values. Like, you can get a modern 0.5 microfarad paper capacitor, or film capacitor, I should say, but it's going to cost you a lot more than a modern 0.47, and the 0.047 isn't going to make any real difference in just about any circuit that would have used the 0.05. In some cases, you can get closer to original values than the most common standard values. Like, most people would select either a 0.033 or a 0.047 to replace a 0.04. But there's also a 0.039 that's available nowadays that would be a little bit closer to the value of the original part. It's always wise to look over the values available and try to pick the best ones. I have over here an antenna blocking my shot. I have over here a large box of capacitors. These are all the paper capacitor values I typically use in my restorations. Up above, I've got electrolytics. The first row is all 160 volt capacitors. First drawer is 2.2 and 4.7. The second drawer is 10, the third is 20, the fourth is 33, the fourth is 47. The next row down we've got 68 and 100 microfarads and some 100, actually some 220 and 330 microfarads. And then there's some drawers in between that are some generally 160 to 250 volt higher microfarad rated capacitors that I've salvaged out of equipment that I've scrapped out, modern equipment that I've scrapped out, that are still good that I keep for oddball circumstances where I need a capacitor that's, say, 400 microfarad to 820 microfarad. And I've got the same capacitor values, the same capacitance values that I discussed before for the 160 volts, duplicated in 450 volts, filling up the lower drawers, particularly the large lower drawers. Radios without power transformers typically use 160 volt caps only. Most televisions, and a large percentage of radios that use power transformers, typically require capacitors somewhere between 250 volts and 450 volts, and for most of those applications I just stick in a 450 volt cap and let it run. Also above that we have a large selection of resistors. DigiKey sells some nice 1 and 2 watt resistor kits that cover everything from 62 ohms to a mega ohm. Now you have to buy 2 kits to get all the values in that range, but it's nice having them on hand if you service a large number of radios and televisions, as I do. Honestly, you don't need all of this stuff. If you wanted to, you could go through the parts list on any given TV or radio that you've just bought, figure out which parts you are going to replace, and preemptively order them up and just have them on hand and install them. I find that with the volume of work I do, it's cheaper for me to buy parts in bulk. Some caps that are common values, like say 0.047 microfarads at 630 volts, I'll buy those in quantities of 100 because I use them heavily. I also have way up top a travel case. When I go on vacations and buy stuff, sometimes I can't resist the urge to fix it, so I just have stuff to fix up equipment right in my luggage. But let's get back to this TV set and change out that next capacitor there. Okay, so this cap is a 25 microfarad at 25 working volts. I don't stock anything that low a voltage, but you can use a higher voltage cap, so here's a 22 at 160. That'll work just fine for the application. So the ground comes off here, and the positive comes off here. You know, there's a nice ground lug right there. How nice would that be, like that? That could work. Let's bend these up a little bit neater. Let's use the pliers to get a nice sharp angle like that. We can just yank this off of here with a little bit of heat to get the solder to let loose. Come on. Let go. There we go. Nice. Okay, let's just situate this here. I've already done 2 of these chassis. Maybe I should do a quick... Okay, change of strategy. We're gonna put this up here like this. Okay, so try that and that and decent. Crunch that onto there like that. Let's just a little lead on there. Okay. There. That's good. Now, lots and lots more. If I'm not mistaken, this... Man, I'm not even focused on what I'm doing with the camera. That's great. So, this cap used to be hooked in like this. We've taken it out. This terminal here that used to be hooked onto is a ground terminal on the terminal strip, and so is this one. So we're going to relocate this cap onto this ground terminal so we don't have to try to stretch the wire way over here where it can't reach. We're also going to, before we install this, we're going to take off the ground terminal for this, if I recall correctly, 0.22 600 volt cap. Try to change that at the same time. Get out of there. Get out of there, you goofy little thing. Okay. Yep. Memory serves. 0.22 at 200. Let's grab one. And since this terminal is a ground terminal and this terminal is a ground terminal, we can move the 0.22 right over to here. It's no different than what the engineers that designed this set back in the day would have done if they had had the modern capacitors we have available then. They would have used these exact techniques to choose where on the terminal strips to connect their new capacitors. They just chose different ground lugs because they were working with caps that had different lead length and lead position on them. So we're going to do the same thing. Just using current knowledge and current parts to slightly change the lead routing while maintaining the original circuit design. Okay, that's in good, that's in good, perfect. Moving on, let's see here, what do we want to go after next, and what are we filming? Okay, so this here's a ground lug. This is the hot lug to, I believe, a 0.22 100 volt capacitor that grounds itself up here. We're going to switch its ground around as well. While we're at it, let's just get to it. Okay, somewhere here we're going to find the lead we want to unwrap. There it is. Down there. Get, I say. And sometimes you gotta scratch the wax off to read it, and that is indeed a 0.22. And yank this one out quick. Are you going to try to make this into a cap speed run? Maybe. I think I've covered enough of the basics to start banging through this. Let's see here. This is a 103, which makes it a .01. That would actually be pretty snazzy if I did it that way, but... Damn it, Tom. Quit wasting time and change the capacitor already. Okay. You asked for it. Oh. So someone clipped this one off at this terminal strip and then tack soldered it back on. This should have unwrapped cleanly, and it did not do that. That should be about right. Now we'll just... toss a little bit of that on there. Okay, let's go after that guy next. One thing that's recommended where possible is to try to install the capacitor so that the labels are easily read by someone looking at the chassis or circuit board that you're working on. So that if you or someone else have to service it in the future, all the component values are easy to read. Just kind of do something to help out the next guy who's going to be working on the set. In case you haven't picked up on it, I'm going for the noisiest cool-looking chair on the internet. This calls for some spaghetti. Yep. About that much. So this cap goes to this ground terminal here. And it's a little bit long of a distance from the other terminal that the capacitor attaches to over here. There's a nice ground terminal right there on the socket next to it, essentially. So we're gonna just yoink this out here like this. Come on, get your... this one is, say it's fine. Okay. So, this cap is an example of a cap where there is not a ground terminal on either end, so we can't really effectively move its connection points without changing a lot of the original wiring of the set, which is a pain in the butt and not necessarily a productive move. So what we're going to do is we're going to do something that some technicians absolutely despise. We're going to try to do a good job of it. The humble J-hook. Now, a lot of people will just put a little bend like this and a little bend like this and just do this and splash some solder on, and it's not a mechanically solid connection, and oftentimes it's not a very electrically solid connection. So what I do is I don't L-hook it like what that really is. I J-hook it so you get a nice little J in the component lead. Then I stick the other component lead, which we're just going to... Then I stick the other component lead, as we're going to illustrate with this thing, into the J, and I close the end of this around the wire to make an eyelet like this that's closed. And when you do that on both ends, you end up creating a somewhat mechanically solid joint between them before you solder them. And when you do that before you solder, it ends up being a better connection all around. See that? That actually more or less holds its position, which is pretty good. And we don't have enough room on that end to J-hook, so we're going to take some spare component wire that we chopped off of a new component that had more lead than was necessary. We're going to reuse that to lengthen the other end. Go. Solder that. Solder this. Solder that. Not the prettiest way of doing it, but it's electrically functional. And that's all that really matters. Where you can be neat, be as neat as you can. Where you have to compromise, do the neatest compromise you can reasonably achieve. Now, it would be possible for me to find some capacitors with slightly longer leads, but I stock what I stock in my part stocks, and sometimes you just gotta work with what you got, so that's what we're doing. Okay, so we've done all those. Let's move on over to here, and let's get rid of this cardboard tube electrolytic. Okay, on to the electrolytics. An overview of electrolytic can capacitors like this one, and this one. Normally, electrolytic can capacitors are mounted with their bottom end, this spot right here, sticking through the chassis so that the terminals are exposed for under chassis wire connection, like right here. So this spot would normally be facing through the chassis like it is here. You can see this is the can that you're seeing on the bottom of the chassis. Modern electrolytic capacitors are single section. This capacitor here is a single 22 microfarad 450 volt capacitor. Canlytics, on the other hand, are fairly rarely single section. You'll encounter maybe one per set. When a television set has multiple can-type electrolytic capacitors, most of those capacitors will be multiple section. So, here's a single section capacitor, a single section can capacitor, to show the wiring. Now, let me zoom in a little bit more. So, as you can see, there is an outer ring here that has 3 terminals. This outer ring is metal, and it's the negative of the can. So the negative goes to this yellow wire here, and the positive of this can goes to this red wire here. Now you can see holes in the brown insulator that the red is somewhat centered within. These other holes are for other terminals if this capacitor were to have been built as a multi-section, which this one hasn't. You can also see that there are symbols carved into the insulator. There is essentially a square and essentially a triangle or V-like shape. And there's also a blank. On a multi-section electrolytic capacitor, these symbols, and lack thereof in this one terminal's case, indicate which section of the capacitor is which. So this capacitor here is just a single 30 microfarad 200 working volt capacitor. But in some cases you'll find capacitors where there is, for instance, 20 microfarad at 160 on the triangle, 33 microfarad at 160 on the square, and 100 microfarad at 25 volts on the blank. Now that would be a fairly typical capacitor for a tabletop 5-tube transformerless radio. But you might find one of those in a television. But it gives you an idea of how to read the terminals on these capacitors. Now, electrolytic capacitors, polarity is a very important concept. You have the can on these can-style capacitors. 98% of the time it is a negative can. There are rare cases where the can will be positive, usually in transistorized equipment with early transistor types such as germanium, where the chassis ground is actually positive and the power rail is actually negative, where in tube equipment it's always the other way around. So you have to get the positive of the new capacitor connected into where the positive of the old capacitor was, and the negative of the new capacitor connected into where the negative of the old capacitor was. If you flip them around and connect your capacitor backwards, best case scenario, you catch it before you power on the equipment. Normal case scenario on new capacitors like this, when you power on the equipment with the capacitor connected backwards, the equipment will be very unhappy, the capacitor will let out significant quantities of smoke, get very hot, and the equipment may also experience a certain amount of damage. Worst case scenario usually occurs when one of these old school can caps overheats and explodes. The new caps, they have pressure relief impressions in the casing that allow the casing to break apart and release the pressure. The old school ones don't really have that as well as the modern ones do, and sometimes what will occur on the vintage capacitors is they'll actually blow out the bottom seal and the can will go shooting off like a rocket. And if a can that large hits you in the face going full force, it could cause some serious injury. So don't connect your capacitors backwards, or at least don't connect your electrolytic capacitors backwards. Once in a blue moon, there are non-polarized electrolytic capacitors. You typically only see those in speaker crossover applications and here and there in some vintage sets, usually color sets, but some higher-end monochromes as well that have electronic centering controls. Sometimes they'll have a non-polar capacitor in the sweep circuitry. And you'll be able to tell, reading the markings on an original capacitor, whether or not it's polarized usually. Non-polars usually say very boldly that they're non-polarized. So now that we've discussed all of that, this capacitor has been removed from the chassis. Its two wires go above chassis, and the red one goes to this rectifier. You can't see it. The red one goes to this rectifier terminal right here, and the yellow one goes to our fusistor, this yellow wire right here. And what I'm going to do is I'm going to connect the positive of the cap, which is the red wire, to this terminal here, the negative to this terminal here, and I'm going to take the, can you see that? The positive to the red terminal here, the negative to this terminal here, and I'm going to take the yellow wire from our fusistor and run it to that terminal and connect the negative terminal to the cap there. So I need a replacement for this 150 microfarad 200 volt capacitor. I don't have that exact part, and I don't have the closest modern equivalent value on hand either. So now we have a lesson on capacitors in parallel and series. So I can get a 147 microfarad capacitor that will be close enough by taking a 100 microfarad capacitor and a 47 microfarad capacitor and putting the two in parallel. And as you can see, the negative one capacitor connects to the negative of the other capacitor and the positive to the positive. And I need to solder these joints yet, but that gives you the idea. I need, in this case, a 200 volt capacitor. So I can use effectively a 200 volt 47, and because I do not have any 100 microfarad caps that are between 160 volts and 450 volts, I'm going to have to use the 450 volt cap I have. It's a little bit more expensive, but it'll work. To save a little bit of money, I can make the parallel replacement out of a 47 microfarad 200 volt. Now, when you put capacitors in parallel, the voltage of the new capacitor that's made out of the two parallel parts is effectively the lowest voltage of either of the capacitors, so in this case 200 volts. Now, when you need an unusually small value of capacitance and you don't have the correct capacitor, or you need a capacitor of a much higher voltage than the capacitors that you have on hand, you can put capacitors in series. When you put capacitors in series, if they're the same value capacitor, let me grab another same value capacitor for visual illustration. If they are the same value of capacitor and you wire them in series, which in this case would be connecting the negative of one capacitor to the positive of another capacitor, ignoring those now tied together leads, and considering the input and output leads of the capacitors only being these two remaining leads. When you do that, you end up with a 400 volt 23.5 microfarad capacitor, effectively, if I were to put these two in series. So if I needed to make a lower capacitance out of these two, I could put them in series. If I needed a higher voltage, I could put them in series. Now, the rule of the capacitance halving only works when they're the same value. When you put two capacitors in series of different values, what ends up happening is that the series capacitance will be 1 over the sum of the fractions that are 1 over the value of the individual capacitors. You can Google series capacitor formula and you should find that formula. It'll show you what the series capacitance would be of multiple different capacitors placed in series. Now, the voltage adding up rule doesn't necessarily work cleanly when you have significantly different values of capacitance in series. Generally speaking, the amount of voltage across each capacitor doesn't split evenly when you have different values of capacitance. You might end up with twice as much voltage across one of these caps than the other one because the value is about twice as much. So, relying on the voltage addition rule when you aren't using capacitors of the same capacitance can be dangerous. Capacitors will explode under 3 conditions. When they are connected backwards, when the voltage rating is substantially exceeded. There's usually a safety factor in the voltage rating on these, but the farther above that you go, the shorter the life of the capacitor is going to be, and if you're substantially above it, the capacitor may fail very rapidly. So if I put 300 volts across this might blow up in a couple of minutes. But if I put 210 volts across it, it might be good for a few years of continuous service. The third condition under which capacitors can explode is when a polarized capacitor is connected across AC voltage. Not very common to have happen by accident, but there are circumstances where it can happen. I remember one particular case where I had a Zenith radio that I couldn't dismantle the chassis because of some recessed bolts I didn't have tools for. The multi-section electrolytic was accessible above chassis and its wires came out above chassis, so I was able to just replace it above chassis. Well, there's bad rubber wiring underneath chassis and an AC line input wire the insulation came off of, and it was in contact with a terminal of the capacitor, putting full line voltage AC across the capacitors in the set, and it would just blow capacitors one after the other, even if I got ones that were rated for significantly higher voltage than the originals. It wasn't until I got in the radio that I was able to fix that problem permanently. Okay, so the single section electrolytic has been replaced with this guy here, and we've also prepped for the first section of the next original electrolytic that we're going to replace by installing this guy here. Right now its negative terminal soldered to ground, and its positive terminal is on a blank terminal that we will run a wire to. Okay, I'm not sure how much footage I lost when my SD card ran out of memory abruptly, but that second can we installed above chassis was a 147 microfarad 450 volt. This can is a 4-section can. Its first section, the circle identified section, is 140 at 350 volt. Close enough. We also need a 100 microfarad at 300 volt. We'll use a 450 volt for that later on. a 20 at 300, and another 20 at 300. So first let's replace that 140 at 350 volt part, which is the capacitor section labeled with the circle, which is this one right here. It's this section right here, so this positive terminal here will be the positive for that capacitor. Now the can of this capacitor is pressed right up against the chassis in normal operation, so it has the negative can part of this capacitor is connected to chassis. And we can even see this lead right here, which is a backup, goes to this terminal right here on this terminal strip, and that terminal is a chassis ground terminal. Okay, so with that lead unhooked, let's flip the chassis back over. That's the positive lead for that 140 microfarad 300 volt cap under chassis. We'll just route the wire right around over here, getting it on the terminal strip with a pair of needle nose pliers. Good enough. Okay. Clean up that solder ball. Route the wire just a little bit cleaner, and done. With that, from this point onwards, my chair will continue to fart. From this point onwards, we are going to have under chassis work until this can and this can have been dealt with. In order to deal with those properly, we're going to want to install some terminal strips. Conveniently, we have one blank terminal right here that doesn't connect to chassis ground that we can use for a positive for one of the 3 remaining new capacitors that will replace the 3 remaining original capacitor sections of this can that are still connected. Now, in addition to using this one empty non-grounded terminal right here, well, we're going to need exactly 5 additional non-grounded terminals that don't exist on terminal strips in this set. To do that, I am going to use new terminal strips. You can go online to Mouser Electronics website and look for terminal strips manufactured by Keystone.
My Kiki, she's stuck in the tree. Hold my stones. Hey, little Kiki. Easy, easy, easy. Atta girl. She'll be fine. She's just a little shaken.
Thank you, young man. What's your name?
My name? Yeah. It's Keith Stone.
Keith Stone, you're so smooth.
Always.
Smooth brewed Keystone Light.
And they make a variety of terminal strips, including this guy right here that has 6 ungrounded terminals, one shortened grounded terminal that they kind of are discouraging you from using, but you could use as a grounded terminal if you solder a rivet eyelet. And I'm going to use one of these 4 ungrounded, 1 grounded terminal strips. And with that, we're going to build up the new terminals for the unit. What we're going to do on this one is we're actually going to truncate it. I think you can buy one in this form factor, but I don't have any in stock, so I'm going to make one by truncating one. We're going to mount it to this audio output transformer mounting screw. Just remove it, slip the terminal strip underneath, and cinch it back down. Now you want to point the end of the terminal strip essentially right near this yellow, or this hole that this orange wire comes through. There we go. That's nice. For our other terminal strip mounting, what we're going to do is we're going to reuse this bolt hole for the old capacitor mounting as a mount point for the other new terminal strip. Okay, that's on there, and we'll just chop the extra terminal off later on, probably. First one I want to do is the one with this resistor on it, because if I keep flexing on this resistor lead, I'm going to have a ruined resistor. I don't want that. Let's see here, that's the blank, which the blank is indeed a 20 at 300 volts. Okay, sweet. So now that we know that, let's start dissecting this further. Give me the wire. Thank you. Next, I want my resistor free. Somewhere with that. Kindly release the capacitor for me. Thank you much. There we go. Now I got stuff to work with. Let's just kind of mash this wire straight with our needle nose pliers. That, and now we're taking advantage of that unused terminal from the original design. And that would be a positive to a 22 microfarad. There's a negative down here and a positive up here. I could also... Let's just bend the leads to give us an idea of reach. Then we'll figure it out. This direction would make... I could make that work. Okay, now we know what direction we're heading on this. And so that negative goes there. Here. Now we can start wrapping the leads around the terminals like so. Come on now. Okay, let's solder that onto there, nice and good. That lead's nicely buried in solder, so it'll have a good long-term connection. There's a big old solder blob covering it up and mounting it down. Okay. Now I got 2 more sections remaining. Okay, so the square mark terminal here is the 100 at 450 volts. Or 300 volts, I should say. We're going to use a 450 volt cap to replace it anyway, so it doesn't really make too much difference. Come on. see what they did. Philco was fairly fond of using wire wrap terminals that don't have a center hole. So usually most of their electronics are wire wrapped and then soldered. Except for the printed circuit boards on this set, the wires that go to the stakes on them are only wire wrapped. They are not soldered typically. These filter capacitor terminals, however, have eyelets, so apparently someone made the decision to do an actual through the eyelet connection, and not before doing the wire wrap, and not a pure wire wrap, and that makes that fun. Okay, so we've got this wire here that comes off of this terminal. And we've got this wire here, which comes off of that terminal there. I'm going to actually take this one that goes to... Man, that's hard to reach. There we go. Let's just pull this wire out of here. And we're going to also pull it off here if it'll cooperate with us. I suppose I could just snip it, but that does... I'll just flex it free. There we go. And wrap that around there. And take our 100 microfarad at 450 volts, and we will hook the negative in to this terminal here. Good enough. Okay, now we can solder that in nice and good, and just like that, that's dealt with. Time for the remaining capacitor. Alright, so we're going to take this 20 microfarad, run to that terminal, and put a capacitor there. So let's get on that. Go. Now, we just need to figure out the orange wire. Just snip it off and get on with it. Maybe. I don't want to give up on you yet. You know what? I do have enough slack. I'm just going to snip it. And I messed up the insulation just a pinch anyway, so let's just clean up the insulation a little bit. There we go. It's nice and clean. Just run that through there. So this capacitor's out and replaced. The last one is this guy right here. It contains a 10 at 450, 20 at 300, and a 200 at 25 volts. So I know I'm going to run the 10 off of this cap to this next terminal here. So in preparation for that, I'm going to do something that I started to do on the other can, which is twist those together a little bit. So yeah, that should work. And we put a little solder around that splice. I have no idea if the camera is focusing or not. Okay. Time to bake us a capacitor layer cake. I should be able to. Roughly good enough. Okay, so which one was the 10? I think it was the square. Let's double check that before we do what we're doing. Yeah, 10 is the square. Okay, let's oh, that's just wire wrapped. Yay, Philco. Let's do it slightly different on each part. I wonder how many employees they had soldering these chassis together, if they had a different person installing each individual capacitor, or if the same tech would just work on the entire thing. Okay, now we just solder that in. The 200 microfarad, I think 25 volt cap, I'm going to route to this terminal over here. The 20 at 450, I'm going to route to one of either this terminal, you can't see it, I'm going to route to either this terminal or that terminal. Probably this terminal. It'll be wherever the resistor lead is happiest going, so let's do that. Come on, you two. You're getting off of there one way or another. And lastly, you, Mr. Resistor. Okay. Let's clean that lead up just a little bit. Pound it out flattish. Or straightish. Whatever works. Okay. That'll go in there just fine. Beautiful. Now just gotta clean these suckers up. This one's not bad as is. We'll clean it up a little bit. Shorten it to the length we need. Ram it in there and tie it off. And clean this one up too because it needs it. And we'll cut off the half of this strip. Well, I won't cut it off because someone might need it someday. This one, it's better to cut off because it interferes with the transformer. Okay, let's get that 20 microfarad in. That's not bad. Just solder the ground and the positive. There we go. Those are both decent joints. Oh yeah, that's on there. Okay, good. Now I gotta find me the volt-turned microfarad. Okay, so I found this 220 microfarad at 25 volt lytic in my used pole stash. And this will be good enough for the vertical stage cathode bypass lytic. Let's just stick that in there. There we go. That basically works. Now what I'm going to do here is I'm going to put it through the rivet eyelets that hold the terminal strip metal to the phenolic insulator. Okay, negative secured firmly. We'll also go after the positive, like that. Readied up the connection for the... You can't see nothing. Well, that's okay. We'll fix it in post. Okay, so this is the lone orange of the vertical output cathode bypass. We're gonna loop it through that there terminal and the insulator eyelet on the riveting eyelet on the bottom of the terminal. Ooh, that cap soldered in nicely. The cap soldered in there nice and good. Put this wire on and effectively Effectively, this cap is... Huh. I guess it came loose from... Oh, because I heated the joint and then I flexed it. Yeah. That's going to do some untoward things, isn't it? Okay, sweet. All the electrolytics and under chassis capacitors that need to be addressed have been addressed. We will figure out this this resistor jumper later on. Next up, we're going to look at how to go after the printed circuit board on top of the chassis. You ever built a ship in a bottle? Neither have I. But I imagine it's something like what that would be. Okay, we have smoke. Where is the smoke coming from?
Be sure to subscribe for next episode to find out where the smoke's coming from.